Right, so yeah, I'm going to talk about the book Proofs and Refutations and the work in that, looking at that through the lens of AI. So my background was an MA in mathematics and philosophy, and then a PGCE in maths education and a few years teaching that at different levels. And then I came to AI, and then shortly after I came to AI, I came across this book, Proofs and Refutations, and it just really rang true for me. So my experience teaching and what students wanted to learn and what they were able to understand and whatnot, it rang true there, but it also very much rang true of what I was learning about in the automated theorem proving community at the time. So in particular, this is the second appendix in Proofs and Refutations, where Lakatos critiques the presentation of mathematics in a very kind of dry, sanitized way, what he calls the Euclidean style, where you're given the axioms and the theorem statements and some concept definitions and whatnot, and then a proof. And you don't really know the history of any of these things, or what's motivated them, why is something defined as it is. And so he's really critiquing it with an eye on education. How does this look to students of mathematics? And I read through this and I thought, if you exchange student of mathematics for mathematician and exchange textbook for automated theorem prover, then we have a critique of what's going on there as well. Because designers and developers within automated theorem proving at the time were looking at this Euclidean way of presenting mathematics, the front stage of mathematics, as it were. So the way of using a theorem prover would be to input some axioms and a theorem statement, wait a little bit, and then you might get a proof back, or it might just endlessly loop, or it might just not be able to find one. There's no connection between the elements of mathematics and with each other. So the arguments that Lakatos makes in this appendix, that the Euclidean style hides the struggle, hides the adventure. There's a complete disconnect between concepts, entities, axioms, theorems, and proofs. So they're all developed completely independently of each other. There's an authoritarian air, and there's a focus on soundness rather than understandability. All of these critiques apply and still do, to the automated theorem proving community, where you don't see the struggle or the adventure. There is no connection between concepts and entities and so on. There's an authoritarian air. You see this system as an oracle in a way, or you're taught to see it like that. And there's a focus on soundness rather than understandability. And so at the time when I was learning about automated theorem proving, this was being taught as a success in AI because it had achieved a lot. It had achieved human-level proofs, human-level mathematics. And that's something that within AI at that time, and even now, it was very hard to do in lots of other fields of AI. Achieving human-level competence is really difficult. So the fact that automated reasoning and automated theory formation and automated theorem proving had managed to do this was a massive success. But at the same time, mathematicians tended not to engage with these systems. They weren't that interested. They certainly hadn't achieved widespread take-up. And so all of the developers and researchers within this field were asking themselves, why not? You know, why isn't our work, which is doing such great things, being taken seriously by the mathematical community? And I think that Lakatos basically tells us why. These are the reasons why not. Other people have said similar things. So Gowers says, if we wish to teach computers to find proofs, it's likely to be a good idea to reflect on how we do so ourselves. Alan Bundy says, conspicuous by its absence has been the use of automated theorem provers to assist with the development of proofs. Among the reasons that mathematicians frequently give me when I ask them why they're not using automated theorem provers are the following. The proofs are too detailed, so too tedious. The systems are not powerful enough to prove novel conjectures. They're tedious, there's no soft skills such as analogy. They're hard to use, and obviously mathematicians don't get training in using them. And they take away the fun part. This is the bit that mathematicians enjoy about math, so why would they want the system to do it for them? At an event that I organised with Ursula Martin in 2012, Mathematicians flagged the importance of collaborative systems that think like a mathematician. So they handle unstructured approaches such as the use of sloppy natural language, the exchange of informal information and intuition that's not recorded in papers, and they engage diverse researchers in creative problem solving. This, of course, was work of cognitive scientists, sociologists, philosophers, and the narrative accounts of mathematicians themselves, which highlight the paradoxical nature of mathematical practice. While the goal of mathematics is to discover mathematical truths justified by rigorous argument, mathematical discovery involves soft aspects such as creativity, informal argument, example, error, and analogy. So I find this distinction by sociologist Goffman quite useful here. So he talks about the front stage and the backstage of activities of everyday life. So, for example, in a restaurant, the front stage would be the part of the restaurant where customers go, where they eat. The staff would, behave a certain way in that area and dress a certain way in that area. And there's, nice pictures on the walls and all this kind of stuff going on in the front stage. That's where the service is provided to the public. And then in the backstage, you've got the kitchen. I don't know if you've ever worked in a restaurant kitchen or been in one. They're very, very different to the front stage. People dress differently, talk differently. It looks very different. It's generally very different. So this is where the services are put together for the consumption. And Ruben Hirsch applied this analogy to mathematical activity, where the front stage is what Lakatos would have called the Euclidean presentation. So all of the lovely proofs, the publications, the public lectures, the seminars, the conferences, all of those sorts of things. And then in the backstage, that's all the activity that goes into producing the stuff in the front stage. So the messy scribblings on a whiteboard or a blackboard, the informal chats between colleagues over coffee, all the mistakes, the dead ends, the things that didn't go anywhere, all of that stuff is part of the backstage of mathematics. And what it occurred to me was that the automated theorem proving society was focusing too much on the front stage of mathematics and not enough on the backstage. So there needed to be a little bit of a switch of focus. And then this led to asking the question, could AI participate in the wonderful dialectic of mathematical ideas, as Lakatos calls it? And what would that involve? So there's two questions here. What is the wonderful dialectic of mathematical ideas? Lakatos offers us some ideas on it. Obviously, that's not complete in terms of the entirety of explaining mathematical activity. There's a long way to go. And even if we can do that, we still have to do the second thing, build a computational model of it. And both of these are really, really hard problems. But I thought I'd give it a go. So this is going back to my PhD work now, which was quite a while ago. I was just starting out in AI, and so that's my excuse if the system's not very good. It's from about 20 years ago, but I thought it'd be really interesting to show you some output from this system, so you could see where I got with it, at least. So it's a translation. So one way of getting to know a work is to translate it into another language. In fact, Lakatos himself did this with Polya's work. And that's hard if you're doing it into a natural language. It's very hard. If you're doing it into a programming language, it becomes really, really tough, and the connection can get looser. Obviously, you have to make assumptions and decisions along the way about what was intended. You're trying to formalize natural language, and that's, you could argue it was impossible to do faithfully. So this is a representation of it. So what we have on the left is just an extract from Lakatos's book, and what we have on the right is a little bit of the code that I wrote for the system to produce a computational reading of proofs and refutations. The code itself was thousands of lines. I'm not actually sure how long, but maybe 10,000 lines or so. It's quite big. So the aim in modeling his theory was to understand the book better, was to try to bring automated theorem proving closer to this human-like mathematics and focus a little bit more on the backstage. and also hopefully to offer a new philosophically interesting perspective on the work, because you are having to fill gaps and make decisions and flesh out details, and hopefully some of the new theory that you produce along the way is of interest to philosophers. So the differences between my computational reading of the theory and his theory, well, there's many, many differences. Here are a few. There's a different focus. So in Proofs and Refutations, the focus is on one conjecture at a time, a particularly rich and fruitful conjecture. What I did was use an automated theory formation program where we weren't going to get conjectures as rich as the sorts that Lakatos looked at. So what the goal was to output an interesting theory, where a theory comprises objects of interest, concepts, conjectures, proof objects, and so on, and it's the collection that you're looking at rather than a single conjecture. We worked in different domains, so partly this was to address the criticism that's sometimes levelled at Lakatos that he bases his theory on only a few case studies. So we thought if we expanded domains, then it's a way of testing whether it runs, whether it works in other domains. And we looked in other mathematical domains, in particular number theory and group theory. And we also looked at non-mathematical domains just to see how it would be, what sort of reasoning we'd get with those. It was one animal data set that we used, we got good results with. If we needed to look at other historical examples for detail, then we did so. And that comes up a little bit in the talk. The communication style of the system that I wrote was very plain. There's no creative flourishes. So in the Proofs and Refutations, it's the work of literature. It's very entertaining to read. And to try to create language like that would have been an entirely different project in natural language creation. So I just stuck to very plain language. The focus in my system was on mathematics purely rather than on philosophy of mathematics. So in Proofs and Refutations, you both get a theory of how mathematical activity evolves and also how the philosophy of mathematics evolves. So within it, he's critiquing methods that have gone before and so on. That would be possible, I think, with the system that I wrote if you ran it at a meta level. So then the theory that it's thinking about is how it produces the theory, the other theory. So we didn't do that, but I think we could have. I doubt it would have been that interesting. Well, it would have taught us things like, this method is productive in this context, but maybe that would have been interesting. So, but we haven't done that. We just looked at mathematical development. And of course, we made many, many simplifications along the way as well. So I mentioned that it incorporated a theory formation program that was called HR, and that was written by Simon Colton. That was the HR were named after Hardy and Ramanujan, who were particular inspirations for Simon when he wrote his system. HR consisted of, it took in objects of interest, so these are entities which a theory discusses. So, for example, in number theory, the entities are numbers. In group theory, they're groups, and so on. It took in concepts, which could just be defined extensionally if they were given by the user. But if HR generated them itself, it would generate a definition, a data table, and a categorization. And the user would input a few concepts to get it started. I mean, literally, usually 3 or 4. And then HR had a series of production rules that it could use to turn one concept or 2 concepts into another concept. And that's how it generated new concepts. So this is an example of how it would represent its concepts that it generated. So the definition, we've got A, B, where A and B are integers, and B is the number of divisors of A, so the tau function. So that's our definition. We've got the data table, which is complete for all of the entities that are given to it. So here it's just got the numbers 1 to 10 and the tau function for those numbers, and then a categorization which clumps them together according to value. So those are the 3 ways that concepts are normally represented. Here's another example. This is a prime number concept. So we've got your definition, the data table, which is just true or false, and then categorization there. So HR usually works empirically. Each time a new concept is generated, HR checks to see whether it can make a conjecture with it. So whether there's another concept in its theory already that has the same data table, then it can make either an equivalence or an implication conjecture, or if the data table's empty, then it can make a non-existence conjecture. And it also has a set of interestingness measures which are used to automatically evaluate concepts and conjectures, and these drive the heuristic search. So there's different ways. You can set it running at the start, and there's different ways of exploring the search space. But the ways of it automatically evaluating its own concepts and conjectures are very useful for guiding the search. You can put it on a best first search, which means it takes its current most interesting concept, for example, and develops that further, and just keeps looping like that. So the way that it evaluates them, and he was inspired by working in maths textbooks to get these. So be it a concept being novel, having a simple definition and applying to many entities. And for conjectures, the interestingness measures included applicability, that's the proportion of entities that the conjecture discusses, comprehensibility, and surprisingness. So a conjecture is surprising. Each conjecture has an ancestor list, so a list of all of the conjectures that were involved in its construction. And if two concepts are conjectured to be equivalent, but they have very few concepts in common in the ancestors list, then that's considered surprising. If they have lots in common, then it's not so surprising that they've got something in common themselves. Right, so I just added the L, the Lakatos, and made HRL. The architecture of the system looks like this. So I followed his terminology in terms of students and teacher, and set up different agents. So these were represented on different computers in the department that I was working in at the time. So each computer was an agent and had a copy of HR, and you could set it running with a variable number of students, and there was always one teacher as well. So the number of students tended to be 2 or 3. So they would have their own copies, their own abilities to formulate theories, and their own input data. We had to be quite careful with how you distribute input data. So this is entities that you start off with, core concepts, which Lakatos methods it's going to apply, which production rules it's going to apply, which interesting measures, and lots of parameters at the start. If you make them too similar, so if you give them all the same data to start off with, the discussion, they all generate the same thing. Well, not quite, because there is an element of non-determinism, so it's not quite the same thing, but they generate very similar theories, and then the discussion's not very interesting. If you give them very, very different data, then they struggle to understand what each other is saying, and again, it's hard to react then. So, for example, if one was in one domain, number theory, and the other's in group theory, it wouldn't really work. So you have to get the right level of difference in the input data so that there's some conflict, some interesting conversation, but not too similar and not too different. And the cycle is that they form their own theory, so they work independently for a certain number of theory formation steps, and they're evaluating it along the way. And then the teacher says, send me your best conjecture or your best whatever at a certain time point. And they evaluate what's the best one and send that in. And then the teacher, who also has a copy of HR, so also can evaluate the agenda that it's been sent, evaluates it in terms of most interesting first, and sends them out in that order for modifications, problems, responses, and all that kind of thing. And then after a discussion phase, it cycles back to working independently for a bit. This is the loop for Lakatos's methods that we used. So at any one point, you can see the possible moves that are available to the agents. That's the agents as a whole. They're not all available to all of them at the same time necessarily. So you might get, say, student 1 proposing the conjecture, student 2 raising a counterexample, and student 3 performing piecemeal exclusion on it, and then the new conjecture, and then it kind of loops back. So this is collaborative, and we're trying to make it as close to Lakatos's book as we can. Yeah, I think I just said all that, actually. So. Yeah, I already said that. Move on from there. So the overall cycle, kind of at a higher level, is, well, the historical data set that Lakatos looked at is up in the top left corner. And then from that, he constructed his theory of mathematical activity, which he represented in the book. From that, I extracted various formalisms as formal as I could. So here we've got the methods, here we've got the whole architecture where all of these students had access to those methods. And then this outputs some results, and then you could keep cycling around and use those results as an input for a new and revised theory, if you wanted to, and kind of keep going through. So 2 questions here. Is the system a faithful model of the theory? And what's the computational perspective taught us? So let's go through the methods a little bit to show you what sort of output we were talking about. So surrender, we did, as I said, we did tend to look for other historical examples just to flesh them out a little bit, because it's hard working from only a few examples. Surrender was quite hard to find examples, because in textbooks they tend not to tell you which conjectures were not taken up, obviously. But this was one, so the first 4 perfect numbers have the same digits. So the first one has 1 digit, the second one has 2 digits, and so on. But the 5th one's a counterexample, and this whole thing was later abandoned. It wasn't modified. It wasn't thought to be interesting enough. So when should we surrender a conjecture? This is how we did it in HRL. Other method flags are set to false. So as I said, each agent was able to perform different methods based on what you've told it can do in the input. If the other method flags are set to false, then it's more likely to do surrender. Or when the number of conjectures which the counterexample breaks is below a user set threshold. So this idea is not quite faithful to Lakatos, but it's the idea that you're looking at an entire theory, which I think is what he was doing, but it just came out in the book. It was so much focused on one particular conjecture. We're looking at if the question is, should we surrender something or try to bar the counterexample, we want to say what other influence that counterexample has on other conjectures in the theory at the time. So that's what that is about. Is this object causing problems in general in your theory, or is it only in this one context? Because if it's in general, we might just want to bar it. Then if it's already been modified, so obviously in proofs and refutations, the same conjecture was modified multiple times. And this did lead to what he called the problem of content, because each time you modify it, you're making its domain of application a bit smaller. So you end up, I mean, if you go to extremes, you end up with a tautology. And we found that with much less interesting conjectures that the system was looking at, if you modified them more than around 3 times, they just became really dull. So we tended to put a threshold on the number of modifications. But again, that was something that the user could input at the start. We tried not to make fixed decisions, but allow the user to experiment as it went on. Or if it's not interesting, if the conjecture is just not very interesting, or if it's less interesting than the average conjecture in the theory, so the focus should be on something else, or if it's not plausible, or if its domain of application is very small. So there's a lot of relationships between these. But those are when we considered that the agents could perform surrender. So here's some output. I'm just going to read it from the screen. So the first student, this system was, this run was done with 2 students and 1 teacher. And the first student had integers 1 to 10 and core concepts, integer, divisor, addition and multiplication. And the second one had integers 11 to 20 and the same core concepts, and they're set to use surrender in slightly different ways. So the teacher requested that they work independently for 10 theory formation steps and send their best near equivalents. So this is something that's almost the case, not quite. The first student found or made the conjecture: for every integer c, there exist 2 other integers a and b, such that a plus b equals b plus a equals c. And it already knew about the counterexample when it made it, because this one had the number 1 in it. So because 0 is not given as an integer, 1 is a counterexample to this. So when the teacher asks for modifications, the first student is able to come back with this. It's calculated that the interestingness is pretty low, and it's, in fact, the other ones are more interesting anyway, so it decides to surrender its own conjecture. So this was one thing about how much loyalty to one's own work should we be implementing. And obviously in proofs and refutations it's much more animated, and people defend and attack and kind of stick with their stance, but and you could make it like this, but for the most part we tried to make them a bit more objective. Okay, so second example, the students both started with integers 1 to 10 and the concepts integer, divisor and multiplication, and they're set to perform surrender in slightly different circumstances. The teacher asked them to work independently for a bit and send their best near equivalents. They both formed, because they had very similar input data, they both formed the same conjecture that an integer a is equal to the number of its divisors if and only if a divides a and a times a equals a. This has counterexample 2, which they both found, but then they disagreed about whether it was interesting or not. Student 1 found that it wasn't very interesting and therefore surrendered it, and student 2 found that actually it's worth working with this still, so student 2 carried on with it. So what you end up with is the students have their individual theories and they have this communal theory, which is all the stuff that they discuss. And then at the end of the discussion phase, they take whatever is interesting to them from the discussion into their own theory and continue to work with that. And the other thing that I should mention is if a conjecture is surrendered, or if an example is monster barred, for example, and the teacher says, right, we're not to consider this as a valid entity anymore, then we had to make a decision about what do we do then with that entity? What happens to it? What is its status? We didn't want to just wipe it out of the theory because it has a history. At the same time, it can't be allowed to carry on functioning as the kind of object that it was previously because it's been barred. So we called it downgrading to a pseudo-entity or a pseudo-conjecture. So this was another list that all of the agents had access to. So this is the stuff that's kind of been discarded during discussion, but they still have access to it. If they think it's interesting, they can always take it back into their theories afterwards, but not during discussion. Okay, monster barring. So this, sorry, I don't know what that's doing there. This raises the distinction between concepts which are ill-defined and maybe intuitive, maybe have an intended meaning, and specific definitions. And the whole method relies on there not being a specific definition. So the extension may not be known and the intention may not be known in order for monster barring to be possible. So it starts with an ambiguous concept and makes it a little bit less ambiguous in some way. It could still be ambiguous. And raises the question of whether monster barrers are guilty of contracting concepts or monster acceptors are guilty of stretching concepts. So in the section on this, Lakatos talks a lot about intention or intended meaning. And again, that was something that we stayed away from a little bit in the implementation because intent is a very difficult thing, maybe impossible thing at the moment to try to model. So we just didn't worry about intent, but we did take ambiguous concepts and try to make them a little bit less ambiguous. So there's two decision points here. Deciding whether to suggest that an object be barred and deciding how to react to such a suggestion. And this is a method where you can very clearly see the dialogical aspect of Lakatos's work because the different definitions are being negotiated and debated. So in our implementation, arguments are made for rival definitions based on the desirability of admitting a certain problem object into a concept domain. This desirability might be wanting to exclude an object to defend a conjecture or include it to attack a conjecture, or exclude it because it breaks many conjectures. Again, we're looking at the whole theory rather than just a single conjecture. Or this last case, we found that sometimes having an object in a theory forces other objects to be counterexamples. And so if you take out that object, then the other objects behave much better. So we called that a culprit breaker. So if you found that something was a culprit breaker, that was much more likely to be barred because it was causing problems all over the place. Just a few other examples that we looked at. The definition of set, so was initially defined as this, obviously led to some problem sets which necessitated refinement of the concept. And the initial definition of prime number as a natural number which is only divisible by itself from 1, which then includes 1, which is annoying because it's a counterexample to lots of theorems and conjectures about prime numbers. And of course you could apply exception barring and say all the time all primes except 1, but it's neater, if you're always doing that, it's neater just to say, okay, look, 1's not prime, and then you can just say in your conjecture statement, all primes. So 1 is now defined as a natural number with exactly 2 divisors, which bars it essentially from the concept of being prime. Other examples from history books is 0 a number. These all violated conjectures and theorems at the time, and they were controversial at the time. There's 1 a number, square root of 2 a number, square root of -1 a number, and aleph null. And we looked a little bit at those and the discussion around them in order to help us to implement monster barring. So when should we perform monster barring? If the object breaks the conjecture under discussion, which otherwise has no counterexample, if it breaks more than the user set proportion of conjectures, or if it forces other objects to break the conjecture. And the other thing we needed to know was how should we respond to a proposal. So if another agent in the architecture wants to bar an object, how should the student respond? And that it responded as follows. So if it voted, it was just done on votes. We made it democratic, which the teacher calculated at the end. But the students decided to vote to accept the proposal if it broke the conjecture into discussion, if it was set to accept the strictest definition, or if it broke more than the user-defined proportion of its conjectures. If the object was not new to the student, so it was already in their theory, then they didn't initially suggest to bar it. But they did sometimes agree with another suggestion to bar it because they could find that they could see that it was causing problems in their own theory. So we tried to implement a little bit of loyalty to one's own data set, but it was prepared to reject things in it if it was causing problems. And then, as I said, the teacher just counted the votes. This was something else. We didn't know what to do. In Lakatos, they just go with the strictest definition each time and keep going. And we could have done that, but because there's lots of interesting debate about whether to accept it or not, it seemed a bit simplistic to then just take the strictest. So we just made it a democratic counting votes sort of decision. And as I said, if the vote did go to bar it as a monster, then it was put in a communal list of pseudo-entities. So how should we perform it? There's this concept and definition distinction where we exploited the difference between core concepts which did not have a specific definition and the developed ones which do. We had 2 types of monster barring. We had vague to vague and vague to specific. Vague to vague, the definition was left unchanged, and the debate was just whether the concept should cover a certain entity or not. And vague to specific started with a vague, an undefined concept definition and ended up with a more specific one, which they got from their list. So a few examples. The first student has integers 1 to 30, and the second one has integers 2 to 30. Oh, there's 3. The third one also has 2 to 30. And the teacher asked them to work independently and then send their best non-existence conjecture. The third one said there doesn't exist a number such that when multiplied by itself gives the same number. So there doesn't exist an n such that n times n equals n. Does anyone have any counterexamples? Yes, 1. And then it found that 1 was a counterexample to 30% of its conjectures. 1 is not a counterexample, it's a monster. And then the first student found, well, actually it's a problem for my theory as well. So I agree, yes, okay, let's bar it. And they all agree, which is a bit boring, but so they end up barring it. The second one, the first student has integers 0 to 10, and the second one integers 1 to 10, and they work for 20 theory formation steps. There do not exist integers a, b such that b plus a equals a and a plus b equals a. Does anyone have any counterexamples? First student said all of my entities are counterexamples to this conjecture. Well, what do you want to do about that? And then this is where it found that there was a single sort of culprit entity which is forcing all of its entities to be counterexamples, and found this thing 0. So it said, right, well, let's bar the number 0. And then they agreed to bar it. Right, exception barring. So in proofs and refutations, this takes 2 forms. You can either generalize from counterexamples and exclude that concept from your conjecture statement, or you can generalize from positive examples and limit your conjecture statement to that. Obviously, this can result in the same conjecture modification, depending on what concepts you've got. Other examples, all even numbers except 2 are the sum of two primes. All primes except 2 are odd. All integers except squares have an even number of divisors. All integers except those of the form 2k can be written as the sum of 2 or more consecutive integers. So we notice here the counterexample barring, where all even numbers except 2. So 2 is specifically named. I mean, you could argue that it's a concept as well, but we call that counterexample barring, where you just name the counterexamples in your conjecture statement rather than finding a different concept to cover them. So we had to think about how we apply exception barring to other types of conjecture. The examples in Lakatos's book are both implications, and exception barring on equivalences and non-existence conjectures looks a bit different, so we had to think about that. And sometimes it results in more than one modification, so particularly in an equivalence, it can result in two conjectures which complement each other. You have 2 implication conjectures, for example. Okay, so some examples here. We've got first student with integers 1 to 10, second one 11 to 50, third one 51 to 60. And the third student says all integers have an even number of divisors. The first student sends back their examples, and the second student, counterexamples, and second student also finds lots of counterexamples and sends those back. So this is now, we call this communal piecemeal exclusion, where they do it together. So they don't just look at their own examples, form a concept, do the modification, and send that back. They're doing it together. They're pooling all of their counterexamples. They're pooling concepts that might cover just the counterexamples and performing modification together. So then they find the concept of squares and form the concept of non-squares and modify it to all non-squares have an even number of divisors. And another example, we have integers 1 to 10 and 11 to 20. All even numbers can be expressed as the sum of 2 primes. Does anyone have any modifications? 2 is a counterexample, and in this case, the student 1 has performed the modification on its own. We can modify it to all even numbers except 2, the sum of 2 primes. And the third one, they have the same information, integers 1 to 10, and these core integers, what do they ask for? Their best near equivalence conjecture. So student 1 forms the conjecture primes are nearly equivalent to odd numbers. Does anyone have any, I mean, obviously it's not very nearly equivalent, but the threshold must have been set quite low for that. The teacher says, does anyone have any modifications? And then there are counterexamples on both sides of the equivalence. There's 2, which is prime and not odd, and 1 and 9, which is odd and not prime. So they find concepts to cover those, and that results in 2 modifications. Right, so lemma incorporation. I'm a little bit aware of the time, I've got so much more to say. This was the hardest one to implement, as you can probably imagine. We had to, first of all, we had to find a way of representing an informal proof in the system, so that didn't exist previously. Then we had to enable the computer system to uncover hidden assumptions, all of which is quite difficult because computers don't make assumptions. We had to try to formalize the surprise that's felt when an example behaves in an unexpected way in a proof. The next ones are a little bit more easy, I think. So given a counterexample, how can a computer program determine whether it's global or local? And how can a computer program perform local or global or hidden lemma incorporation? So we went back to the same domain to implement this, and we represented the proof using a series of HR's conjecture-making mechanisms, an argumentation way of presenting the proof. So you can't just have a list of conjectures, you need to say the relationship between them for the proof, and user functions where you input information at the start of the run so that it's able to construct these conjectures that you need for the proof. So that's how we did it. It was using a mixture of techniques. And as Lakatos said, this method, the lemma incorporation, reuses exception barring because you're incorporating a little bit of one of the conjectures in the proof into the main conjecture. That's it, exception barring. So we reused the methods for that. Hidden assumptions were found in 2 lemmas and caused surprise in different ways in the book. The first one, so it was both about the cylinder. The first one is when you remove the face, if you remove the jacket and you're left with 2 circles on the board, you're left with something that it's not a counterexample. It hasn't violated any of your proof conjectures, but it has a quality, it's missing a quality that all of your other examples had when you did it, which was to result in a connected network. And that wasn't explicit in the proof, but all the other examples had that quality, and this one doesn't. So it's, this is the idea of an entity being surprising with respect to a certain conjecture. It's surprising. It hasn't broken it, but it's surprising. And the second one was caused by non-meaningful terms. So this was in the discussion of this lemma where that says any face that's dissected by a diagonal falls into 2 pieces. Well, there are no diagonals on the circle, so it's vacuously true. It's not a counterexample, but it's still, there's something a bit odd about it. So we wanted to capture the idea of an entity being vacuously true, some property. We had to, this is something that was sort of obvious in the human case, and then when you come to implement it, it's a lot harder than you realize, because the type of entity that is the counterexample changes as you go through the proof. So it's the same thing. So at the beginning, for the main conjecture, the global counterexample is a polyhedron. And then you do something to the polyhedron and it ends up as a network. So now you're not talking about polyhedron anymore, but you've got a network, and that network might be a counterexample to one of the lemmas in the proof. So while it's clear the connection between that network and that polyhedron is clear to humans when you're cycling through the proof, to a computer it's not. So something could look like a global but not local counterexample because it hasn't made the connection between that polyhedron and that network, if that makes sense. So we had to implement a way of connecting these different entities which were changing their type as you cycle through the proof. I think I said it at the bottom. It may appear that we have a counterexample that's global and not local, since a polyhedron can only be a counterexample to conjectures about polyhedra, not to conjectures about graphs. Okay, so when the student receives a proof scheme from the teacher, it reconstructs the local conjecture and all of the local lemmas in the proof. When it does this, it looks to see whether it's got any counterexamples, and if so, it reconstructs an implication conjecture, which the teacher sent as a near implication. So it's because it already knows about the counterexamples, or an equivalence as a near equivalence. if the student does have a counterexample, it needs to determine which type of lemma incorporation to perform by determining which kind of counterexample it is. And if the counterexample is global, then the student first tests to see if the same counterexample violates one of the local lemmas. Yeah, I didn't put in illustrative examples for this, but there are some in the thesis if you're interested. It's just they're quite lengthy and the representation is quite difficult. But we can talk about it maybe. So, coming kind of back around to evaluating the computational interpretation, we fine-tuned the methods, so we experimented with different values of the parameters and different ways of, for example, distributing data between the students, how long they should work for independently, which methods they should perform and how should they perform them, where the objective measure was an interesting theory. So we tried to find out what were the optimal values for all of these parameters to get an interesting theory. We published the work in Automated Theorem proving venues, so hopefully it's of interest to them. We also implemented a kind of a cut-down version, which didn't have the social aspect, but did incorporate exception barring, called Theorem modifier. I'm just going to talk about that in a sec. And that was quite successful. And thirdly, we evaluated the extended computational theory of mathematical discovery according to philosophically interesting criteria, such as generality, explanatory power, and non-circularity. So that was HRL. I'm aware of the time, so I'm going to wrap up quite quickly, but there's just a couple more things. The theorem modifier was a system I just mentioned. This, so A is a set of axioms and C is the conjecture. And this is what you normally input straight into a theorem prover, such as Otto. That's an automated theorem prover. So Otto is a third-party piece of software, and so is MACE. That's a model generation system. And so normally you'd input A entails C into Otto, and it would either output the proof or or not. But that's all. It's yes or no, kind of, with an accompanying proof, if it's yes. But this, on the other hand, we input them into TM, the theorem modifier system, which interfaced up to Otto to ask it to either prove it or prove the opposite or prove it in the trivial case. If that was successful, then it was output. If that was unsuccessful, then it interfaced up to MACE to ask for supporting examples and counter-examples. And then we got a list of those, and then that interfaced with HR, which produced a theory of those supporting and counter-examples. And also, then it sent that theory back, and the theorem modifier used Lakatos's methods to modify the initial conjecture into, well, A plus M, so that's modification, entails C. So that's a modification of it, and then Otto sent back proofs of that if it could. And this was quite successful. So we invented non-theorems from the thousands of problems for theorem provers, that stands for. And it produced valid modifications for 83% of them, with an average of just over 3 per theorem, per non-theorem, sorry. So, and here's an example of one that it found. To us, it feels more satisfying for somebody using the system to say, can you prove this? No, but I can prove these other things which are a little bit similar, and they're connected in this way. That seems like a more interesting answer than just no. But we haven't done tests on mathematicians to see whether that's what they think as well. We also looked at proofs and refutations as a dialogue game, and I'll just leave you to, well, you can look at the reference if you're interested, or speak to me about that. So that's, these were our questions that we'd have to answer in order to see whether AI could participate in the wonderful dialectic of mathematical ideas. Those were our attempts in building computational models of this dialectic that Lakatos described. We've also, kind of in the intervening years, tried to answer the first question a little bit: what does human mathematical activity look like? And we've really drawn on this, on these online mathematical projects like Polymath, and we've started to use these as really rich data sets of backstage mathematical activity. And I think, well, you guys will know better than me, but I like to think that Lakatos would be really delighted by that, that all of this data now online, freely available, freely searchable, on how people collaborate in order to prove theorems. That seems like exactly the sort of thing he would have loved. So we were very pleased when that started happening, and obviously it shows the difference between the front stage and the backstage very, very clearly. So I guess because of the time, I'll just kind of more or less wrap up at that point. I was going to talk a little bit about what we've done there, but I can skip that bit. Just to say that for us, these are provided really great data sets to test some ideas on what mathematical activity actually looks like. We've looked at what are the patterns of communication, and we've tested to see what kind of Lakatosian reasoning we can see in these dialogues. We've looked at what they talk about, how do they, being mathematicians, how do they explain things, and what do they value. So this was our, I will skip this, I think, because of time, but this is an example of Lakatosian reasoning, someone surrendering. Here's a counterexample, monster barring. And yeah, I'll skip, but you can just quickly see some of the way we've analysed what people talk about and what sorts of things are they and how do they all fit together. And this is one we did on how is explanation used. We tested these hypotheses and what do people value, what do mathematicians value. And we looked in both the front stage there with the articles and the reviews from the Journal of Algebra and the backstage in Math Overflow. So apologies for skipping that bit, but I want to leave lots of time for questions. This is just a little summary of some of the work that we've done in this field that I've talked about. So mostly I focused on this first column here. How do mathematicians communicate? That was the data used. Lakatos obviously got that data, performed the rational reconstruction, got the set of heuristics, and then we did the final bit. And then the other ones, we've done all of the steps ourselves. So to conclude, can AI participate in the wonderful dialectic of mathematical ideas? Well, the mechanisms by which research maths progresses, as messy, infallible, and speculative as this may be, can be usefully studied via analysis of informal mathematics. Computer support for mathematics, such as computer algebra or computational mathematics, has typically been for the front stage. A second approach is to focus on the backstage and try to extract principles which are sufficiently clear to allow an algorithmic interpretation. And the study of mathematical practice provides a starting point for this work. Conjecture and concept generation are subject to rationality as well as proof, and therefore systems can be developed which integrate these theory development aspects alongside proof generation. And extending the power and reach of Math Overflow or polymath through a combination of people and machines raises new challenges for artificial intelligence and computational mathematics. And finally, likely mathematical elements of a maths social machine would include technology for going beyond the linear structure to capture the more complex structure of a proof attempt or to represent diagrams, automated theory formations which automatically invent concepts and conjectures, and the importance of collaborative systems that think like a mathematician. So that's my references, and I'll finish there. Thanks.